All right, hello everyone. My name is Ryan Lau. I'm a JAXA ITUF fellow at the Institute of Space and Astronautical Science in Sagamihara, Japan. And today, I'm going to talk about my research on revisiting and resolving carbon-rich Wolf-Rayet dust factories with JWST. So, a Wolf-Rayet star is a descendant of a massive O star. They're characterized by very high luminosities, very hot photospheric temperatures, strong winds, and also very high mass loss rates. And so you wouldn't really think that this is an ideal environment for dust formation, yet there is this specific subset of Wolf-Rayet stars called carbon-rich Wolf-Rayet stars that appear to exhibit dust formation. And so what appears to be the key mechanism to enable this dust formation is the presence of a binary companion. And when you have this, you can get colliding winds between the two winds of the binary stars, typically the Wolf-Rayet and an O or B type star. And then you get the right conditions to form dust in this wind collision region as the material flows down this the shock cone from the wind interface. So not only can they form, is it nice that they can form dust, but we find that they can actually be prolific dust makers. So in the study that we published a little over a year ago, we characterized the dust production rates from the Galactic dusty WC binaries, and we found that they can exhibit dust production rates up to 4 × 10⁻⁶ solar masses a year. So to put that into context, all the AGB stars in the LMC produce around 1.4 × 10⁻⁵, which is only a factor of 2 more than this, just a single carbon-rich Wolf-Rayet binary system. So that exhibits how significant these can, how much dust these things can produce. So my interest in studying them is as potential dust factories in the early and local universe. These are massive stars, they evolve, descendants of massive stars, so they evolve very rapidly. So you would expect to see them, and presumably they could form some of the first dust. So what we did in this paper, IR2022, we ran some binary population spectral synthesis models, and we incorporated dust production into them because the binary companion is important in understanding their dust formation. So we concluded that WC binaries should be an important source of carbon-rich dust at metallicities greater than about half solar, so at around an LMC metallicity. So where do we go from now? So of course, there's further questions that we want to address. WC binaries haven't been as well studied as other more popular dust-producing sources like Mikako had mentioned, so like AGB stars and supernovae. So there's some questions that we still need to address about the dust production from these systems. So for example, do we understand all the dust formation modes from WC binaries? Is it possible you can get dust formation in single Wolf-Rayet stars? Are there other subtypes of Wolf-Rayet stars that can form dust? We're not quite sure. Also, there's questions about the dust formation in chemistry. How exactly does dust form in this hostile hydrogen poor environment? So in order to answer these questions, we're using a slew of ground and space-based infrared observatories to pursue observations. So we've been using the VLT, Subaru, this Palomar-Gattini IR survey telescope, and also Spitzer to answer some of these questions. And this is just an example of some of the work that I've been involved in. So this is nice, but what's next? We need JWST to further these observations, and I'll talk about that in these next slides here. All right, so I'm one of the PIs of the early release science program with the James Webb Space Telescope. So early release science is composed of, there's 13 teams that are selected to obtain some of the first data with James Webb. And essentially the goal is to educate the community rapidly on the key observing capabilities of James Webb. So it's our role to rapidly get data and then demonstrate what the observatory is capable of in its 10 to hopefully 20-year lifetime. So I'm the PI of this WR Dusters team. That's what at least I call us. And we are composed of a very great team of international astronomers, theorists, and instrumentation experts from around the world. So it's been a great pleasure working with everyone on this team, many of which are in this meeting. So just kind of a illustrative summary of what we're trying to do with James Webb, we want to investigate WC dust formation chemistry of these systems. This is difficult to do from the ground, so we can resolve them from the ground in the mid-infrared, but we can't quite get the sensitivity to get spectra, which is key, resolved spectra, which is key. So one thing that we're looking at, or two instrument modes that we're using, is the aperture masking interferometry mode on NIRISS, and also the medium resolution spectrograph on MIRI, which is the IFU. And so we're using these modes to study the composition and formation of dust from Wolf-Rayet stars. We'll also be using the MRS and the MIRI imager to study how this dust evolves as it propagates further away and slowly integrates with the surrounding interstellar media. So very important properties to try to assess if we're considering these as important dust producers. So one of our targets is WR140, which has been referred to as the Rosetta Stone of colliding wind binaries. And so that's because it's been so well studied. We know that it's a WC7 type Wolf-Rayet star, and it has an O5 supergiant companion. It's located at a distance of about 1.6 kiloparsecs and has a very well-defined period of about 8 years. And so these systems are kind of interesting because it's the eccentricity that causes it to form dust episodically as opposed to continuously. And so the reason, or what that causes, is this segmented arc of dust that forms only when these stars are going through periastron passage, so at closest approach. And so we get something that looks like this. This is an image that we took from comics a couple of years ago. And you can see the dust arc here. That was formed in about around 2017. And here's the central WC binary, so the carbon-rich Wolf-Rayet star and the O-star companion. And so because it's been so well studied, it makes for this ideal laboratory for investigating colliding wind dust formation and an ideal target for James Webb. So we even got some terrace observations. So I believe this is the highest spatial resolution observations of this source. This is from near-infrared observations, and this data reduction was done by Thane Carey from NAOJ and also NASA Ames. And so we have some really nice data on this, observations of this. The one kind of interesting side note that I wanted to mention about this and why it ties into this IR2022 meeting is that it was actually a Slack message from Thane in the previous IR2020 meeting, who reached out to me and asked if I need help reducing our data, and we did need help. So this was a nice collaboration that formed out of that previous meeting. All right, so what's really nice about these ground-based observations is that they're essentially enabling us to plan and to conduct our early science with James Webb. So for example, here's the image from comics on the left, and on the right, this is a simulated observation with the MRS, the mid-infrared IFU on James Webb. So we're able to use the information that we can get from ground-based observatories about the morphology, the SED, what the continuum looks like from the stars and also from the dust. And we can get a good picture of what we expect to see. So this may not look super impressive side by side, but the important thing to note out, right, thanks. The important thing to note out is that this image on the right, each of these pixels will correspond to a 5 to 28 micron spectrum, which is exactly what we need to accomplish our science case. And that is to obtain the first resolved spectrum of WC dust. And then we can use this to develop a spectral template to trace this WC dust emission in the ISM of other galaxies. Okay, so in my last minute, I wanted to talk about some of the technical goals of our ERS team. As I mentioned, what we're trying to do is to demonstrate the capabilities of James Webb. And we've heard throughout this entire meeting that there's lots of interesting objects that people will want to point James Webb to, especially IR bright sources like AGN Tori, YSOs, protoplanetary disks, and massive star ejecta. So our key technical goal is how well can we detect this faint extended emission around bright sources with James Webb. And one of the tools that we're developing is this MIRI Psf Subtraction, which is developed by one of our team members, Yanis Argyriou from KU Leuven. So we will need this, and I imagine other people will need this too. So if you look on the left, this is at 18 microns, where the resolution is not as great as it is at shorter wavelengths. But we're able to implement this Psf subtraction and bring out the emission that's kind of close into this bright central source. And so this is going to be a critical tool for our science, and we imagine for other science cases as well. Let's see, so I'm running a little short on time. I just want to mention this since we brought it up earlier in the week. We're also observing WR137 using the nearest aperture masking interferometry mode. And so on the left, you see the interferogram from simulated data. And on the right, you see the reconstructed image using squeeze. And so Joel Sanchez Bermudez has been a key member in pushing this image reconstruction. And so this is one of our other deliverables that we're planning on providing, this kind of data analysis and image reconstruction guide to make this more accessible for people to learn how to use with James Webb. Okay, I'll just leave on my summary slide, revisiting dust production from WC binaries. So we find that these are interesting and could be important and early sources of dust. And we have this ERS program where we are exploiting the high spatial resolution from ground-based infrared observatories to push early science and the capabilities of James Webb. Okay, sorry, I'm a little bit over, but I'll go ahead and take questions. Thanks.
Thanks for that really nice talk, Ryan. I've got a question from Steve Otel.
Yes, so Ryan, we've been observing with the LBTI WR140, 125, and 137 since 2017 with Gerd Weigelt. You may be aware of that because he's one of your collaborators, obviously. Those are super easy targets for us, and we've been observing them about twice a year since the periastron passage. So Gerd is mostly interested in the dynamics of the shell from the LBTI observations, as far as I understand. But we do have a 3 to 5 micron IFU that we can use, and those, as I said, those are super easy targets for us. Is there any merit in taking like R40 or so spectra of those resolved spectra of the LBTI?
Yeah, absolutely. Between 3 to 4 microns. So
Yes.
that would be
3 to 5.
Yeah, 3 to 5 microns. Yeah, that'd be great to see if there's any 3 micron pH or UIR band feature in that wavelength range. And plus, that would be extremely complementary to our Charis observations. So this is actually, like 1 to 2 micron kind of integral field spectrograph observations of that dust in the near infrared. So yeah, that we should definitely talk about that because that would be really interesting.
Yeah, so all 3 are reasonably well resolved, and maybe Gerd hasn't been excited about the integral field spectroscopy so far. I've tried pushing him, but maybe if you can get in touch with him and see why exactly and what his reasoning is and what you can do, that would be super exciting for us.
Yeah, I'll push that for sure. Thanks, Steve.